Hello, everyone. My name is Alexander, and today I'm going to talk about a novel algorithmic approach to Bayesian logic regression. This is a joint work with Geir, Storvik, and Florian Frommlet. And we would like to begin the webinar with the sincere gratitude to the editorial board of Bayesian analysis for letting us have our paper published as a discussion paper. We would also like to thank all of the discussants for their thought-provoking, interesting, and somewhat challenging questions, comments, and remarks. And we will begin today's talk with the general introduction into the Bayesian logic regression model, followed by the description of the GMJ-MCMC inference algorithm that we developed. Then we will provide some simulation study and sensitivity analysis, and finally address some real data examples of QTL mapping, Arabidopsis, and Drosophila. And so the model. Consider a set of binary predictors x1 to xm and all possible logical combinations of those predictors using and, or, and not operators, which we further call trees. Denote via val to be all of the leaves or individual predictors that are built in those trees, and then consider that the size of the tree S is defined by the cardinality of the set of its leaves. Then we can define a logic regression model and consider responses y, which come from some probability distribution f, parameterized with the mean parameter mu and the dispersion parameter phi, where the mean parameter is modeled with respect to a link function to some linear predictor, which consists of an intercept and up to q different logical trees, where we are considering here all of the trees which have size up to C max. For each of the logical trees, we are introducing the beta coefficient and a binary indicator gamma, which switches the tree on and off and allows us to perform model selection. And this creates an elegant way to model meaningful interactions between binary predictors. In addition, we have a very natural way to describe for describing the importance of individual trees via the posterior marginal inclusion probabilities. And whilst today's talk is going to be mainly focused on the Gaussian and Bernoulli regressions, the idea is much more general and can be applied to broader classes of models. And in the rejoinder, we are going to present, for instance, the extension to latent Gaussian models. And a natural example of the logic regression is QTL mapping, where we consider genetic markers to be associated with some trait of interest y, and consider that we have n genetic markers xi, which are defined by the combination of recessive and dominant alleles. Then we have three different options to define each marker. We can have a combination of two recessive, two dominant, and a recessive and a dominant allele, which means that we need to define two dummy variables to describe uniquely each individual marker. And then we can build logic regressions based on those dummy variables. The situation becomes a little bit simpler for the backcross designs when one only has two genotypes, either the combination of the recessive and dominant or two dominant alleles, and for the recombinant and breed lines where one only considers homozygotes. And whilst for the fixed gamma and the fixed selection of logical trees, the solution is really straightforward. Both in the frequentist and the Bayesian context, we definitely know how to make inference on generalized linear models. The model selection problem becomes much more complex. So we have that the number of potential models grows super exponentially with the size of the trees. And hence we have some statistical challenges, in particular, how to penalize for the complexity of the trees in a way to have control over the false discovery rate and still get reasonable power of detecting individual logical trees. On the other hand, we have quite some algorithmic challenges. We have an extremely high dimensional model search problem with many local extrema, which might be sparsely located in that model space. In addition, we have some problems in specifying the logical trees. We have a lot of Boolean equivalences between different expressions because of the De Morgan and distributed laws. In addition, we have non-Boolean equivalences of different logical trees if they share the common beta coefficients. So for example, the expression of x1 or x2 minus x1 and expression of x2 minus x1 and x2 are going to be equivalent in an algebraic way. In addition, the approach suffers from potentially extremely strong correlations between non-equivalent trees. So for example, if we have subtrees and supertrees of exactly the same tree, those can be extremely correlated, even if the individual leaves are independent marginally. And we have to deal with these issues somehow. In order to complete the Bayesian specification of the model, we're going to specify the model and parameter priors, and we will begin with the former. So consider M consisting of individual gamma components to be associated with individual models. So values of 0 and 1 of individual gammas are switching on and off different trees in the logic regression, and hence are uniquely defining 2 to the q different logic regression models. Also consider A to be some scalar from 0 to 1, and K max to be another scalar, which is defining a maximal number of active trees in the model. Then the prior for the models looks as follows. So here we are first introducing some constraint, which is not allowing having more than K max trees in the model. Additionally, we have this product f rho of gamma j, where rho of gamma j is a form A to the gamma j times C of Lj, where C of Lj is some non-decreasing measure of complexity of logical trees. And here, if gamma j is equal to 0, then we are not introducing any additional penalization in the prior, whilst when gamma j is equal to 1, then we are introducing this penalization of the form A to the C of Lj. And the particular measure of complexity that we have chosen is of the form that A to the C of Lj is going to be inversely proportional to the total number of trees of size Sj. And then we are approximating this number by means of disregarding the trees that include the same leaf more than once in order to have more computationally efficient algorithm. But even from this somewhat crude approximation, we can clearly see that the number of trees grows exponentially in the size, which means that the total number of models grows super exponentially in the number of potential leaves in the trees. And this is a little bit complicated in terms of computations, and we are going to deal with these issues somehow afterwards. To complete the specification, we also have, of course, to consider the parameter priors. And the first choice of the parameter priors is the recommended priors for generalized linear models, which are mixtures of G priors, where we consider an inverse and proper uniform prior for the dispersion and alpha, and a joint Gaussian prior for the beta coefficients, where we are introducing this G hyperparameter, for the transform value of which we put truncated compound hypergeometric hyperprior. And the particular choice of the parameters of this hyperprior leads to the robust G prior. Another option that we consider is the standard Jeffreys prior on the regression coefficients. Okay, so now we're done with the specification of the model, and we can try to consider the algorithmic approach. And so in order to compute the posterior marginal probabilities of individual models, we can simply rely on Bayes formula, where we are using the marginal space of models. So in the numerator of this formula, we have the product of the marginal likelihoods and the prior of the model of interest, whilst in the denominator, we have the sum of the marginal likelihoods times the prior across all of the models in the model space. And for the Gaussian responses, we have exact tractable values for the marginal likelihoods. For other generalized linear models, we have to rely on some kind of Laplace approximations, integrated Laplace approximations, or integrated nested Laplace approximations. But the problem here is that the cardinality of the model space, omega, is extremely large. And so we have to deal with these issues somehow, because we cannot physically enumerate all of the models, provided that we have limited computational resources. And in order to resolve these issues, we have suggested a GMJ-MCMC algorithm, which approximates the posterior model probabilities by means of considering only subsets of the models in the denominator of the Bayes formula. But we want to do this also in the way that asymptotically, the algorithm lets the subset converge to the full model space if you run the algorithm for long enough. And here we also have to take care of that. We're trying to include as many of the good models in the denominator as possible. And by the good models, we mean that they have significant contribution to the denominator of the Bayes formula. And we would like to save computational resources, to avoid visiting models with the zero value of the marginal likelihood times the prior or close to zero value as much as possible. Also, again, using Bayes' formula, one can easily compute the marginal inclusion probabilities, which can allow us to measure importance of individual trees in our Bayesian logic regression model. And now I'm going to deal with the algorithmic details of GMJ-MCMC algorithm. And back in 2018, myself and Geir Storvik introduced a mode jumping MCMC algorithm for variable selection for generalized linear mixed models. There, however, we can only consider fixed model spaces of linear models where we have up to p potential explanatory variables, and we have all of the variables defined in advance, and hence we have to do the p different models. And the only problem that we are resolving there is that we are creating an MCMC algorithm, a proper MCMC algorithm, that is capable of moving between local extrema of the marginal likelihoods times the prior. And so this is done by means of, with some low frequency allowing to make large jumps in the model space, followed by local combinatorial optimization and randomization around the new modes. And then the solution to this proposal is either accepted or rejected in the way that we can satisfy the detailed balance. And hence the ergodic probability distribution of this algorithm actually corresponds to the true posterior probabilities of the models. But unfortunately, we can't apply this algorithm directly for the context of logic regression, because we cannot specify in advance the model space. We have seen that the number of trees is already exponential in the number of potential leaves in that trees, so that we cannot even specify all of the trees for the problems of reasonable size. And hence, we suggested a solution of amending the MJ-MCMC algorithm in the settings of the genetic algorithm, which updates population of features or trees of finite size. Before that, a small recap on the MJ-MCMC algorithm. So once again, with some low frequency, we're allowed to make large jumps to a new part of the model space, followed by local combinatorial optimization and randomization. And then we are either accepting or rejecting this solution and also satisfy the Metropolis-Hastings detailed balance equation. Now we can proceed with the genetically modified algorithm, which considers populations as 0 to St max. Each of the population has a finite set of D trees from the full Bayesian logic regression model. And we begin with initialization of the initial population using the best single leaves. And then we use some evolutionary dynamics to generate further populations. And so what we are doing is that we are allowing for several genetic operators to update our populations of features. And the first operator is the deletion operator, which removes the unnecessary bad trees from the current population. So this we are doing for all of the trees which have the marginal inclusion probability approximation below ρ-del. And we are deleting those trees with probabilities proportional to 1 minus the current approximation of the inclusion probabilities. Once we have deleted some of the trees, they can be replaced by the new proposals, and we suggest several operators to create those proposals. And the first operator is the crossover, which selects 2 of the parents from the current population, then randomly takes complements to those, and combines the resultant trees with either logical AND or. Then we have a mutation operator, which selects 1 parent from the current population and another parent from the sets of leaves which did not make it into the S0, and then combines them either with AND or operators. And hence we can let the algorithm be irreducible. So those leaves that didn't make it to the initial population can come back in the model space and can start to build new trees right away. We also have a reduction operator, which selects 1 parent from the current population and then deletes some of the leaves from that parent. Further, the resultant subtrees are being merged with either AND or operators. And so we initialize with S0. For every population, we run a fixed number of steps of MJ-MCMC algorithm, and then we propose a new population of features. For the final population of features, MGMCMC is run until somewhat more unique models are visited, and this allows us to get some posteriori approximations of the marginal inclusion probabilities and posterior model probabilities. We also have suggested embarrassing parallelization of the algorithm based on CPUs, and the resulting probabilities can be either merged using the renormalized formula that we have seen beforehand, where we are simply using all of the unique models from all of the threads in the denominator of the bias formula, or we can use some specific weighting schemes to get the posteriors based on the parallel runs of GMGMCMC. Finally, we are done with the algorithmic approaches, and we can try to convince the listeners to that this is not the most senseless approach to use for logic regressions. And we considered some simulation study where we generated data from data generative model consisting of an intercept and some chosen trees with some chosen signal levels and also some chosen noise level. Based on those simulation studies, we would like to evaluate the individual power of recovering these selected trees, the overall power, as well as the expectation of the false positive number, the false discovery rate, and the total number of the wrongly detected leaves in the simulation study. We considered 6 simulation scenarios, 3 with Bernoulli responses and 3 with Gaussian responses. And for the Bernoulli responses, we could compare the approach with MCLR and FBLR, which have previously developed Monte Carlo Markov chain algorithms for inference on Bayesian logic regression. And the first 2 scenarios were actually taken from Fritsch, and now considering 3 two-way interactions. The third scenario here is a little bit more complex and includes 3-way and 4-way interactions of logical predictors. And on these binary responses studies, we could show in the paper that GMGMCMC outperformed the older approaches uniformly in terms of the evaluation metrics that we defined in the previous slide. For the Gaussian responses, we addressed 1 scenario with 3 two-way interactions, 1 scenario with also a 3 and a 4-way interaction, and one more complex scenario having several 4-way, 3-way, 2-way interactions and single-leaved trees. But today, we're going to only look into the details of scenario 5 without loss of generality, where the results are pretty much the same as for other of the scenarios. And so here we simulated 100 replicates of the data consisting of 1,000 observations on the responses and 50 covariates, which are marginally Bernoulli distributed with the success probability of 0.5 and are independent here. We also simulated the responses from the Gaussian distribution and the dispersion equal to 1 and expectations defined below here. So in the expectations, we have some influence on 1 single leaf, 1 tree consisting of 2 logical expressions, 1 3-way interaction, and 1 4-way interaction. And after running the GMGMCMC algorithm on 32 cores for these 100 replicates of the data, we could evaluate the power of recovering the individual trees, and we can clearly see that the power is very high for at least 1-way, 2-way, and 3-way interaction. We have a somewhat slight drop for the 4-way interaction, but still the power of recovering this complex logical expression is still on the level of around 90%, whereas the overall power is around 96 to 97% for both Jeffreys and robust G priors. The false discovery rate is controlled on 0.1 level, and the number of false positives is around 0.3 on average per replicate of the data and per run of the algorithm. And actually, most of the false positives that we see here were coming from the subtrees of L4, which also makes sense. In 100 runs, only 2 wrong leaves were detected under the Jeffreys prior, and 5 wrong leaves were detected under the robust G prior. Further, we provided some sensitivity analysis of the results to study how varying size of the signal would, for example, change the power of detecting individual trees of different complexities. And in this scenario, we considered multiplying all of the beta coefficients for the data generative trees by a factor k, which was varied from 0.05 to 1, having all of the other parameters kept constant. In the second sensitivity analysis, we pretty much did the same, but we were changing the sample size. So we kept the betas from the original simulation scenario 5 and changed the sample size from 100 to 1,000 observations, having all the other parameters kept constant. And actually, those two scenarios are somewhat complementary. I mean, by means of increasing the sample size and having the same effect size, we could reach exactly the same result as increasing the effect size, having the sample size fixed. And then we also studied the sensitivity with respect to the population size of the GMJ-MCMC algorithm, where D was varied from 15 to 150. And finally, the last scenario in the sensitivity analysis was dealing with the misspecified leaves in 3L4, where we replaced one of the leaves from L4 with a misspecified leaf having a correlation to the true leaf varying from 0.1 to 1. And in cases 2, 3, and 4, all of the relevant parameters were increased uniformly in 10 steps. In all of the cases, Kmax was set to 20 and Cmax was set to 5. We performed the sensitivity analysis with 10 runs or 10 simulations per each individual parameter value. This can be not sufficient for having extremely high resolution estimates of the power, but at least this gives some illustration of the general dependence. And then we depict the results for the Jeffreys prior in red, and the results for the robust G prior are drawn in blue. Here we also are only presenting the results for the forced tree, whilst the results for all of the other data generative trees can be found in the supplementary materials to the paper. And as we can clearly see here, as we would have expected, both for beta 4 effect size and the sample size, we see that, I mean, as we increase the effect size, having the sample size fixed to 1,000, we gradually are reaching perfect power. And of course, we need some strengths of the signal in order to be able to detect this complex four-way interaction of binary predictors. But exactly the same could be achieved by means of having this effect size fixed and increasing the sample size, which answers some of the comments from the discussants who were wondering why we were using such a strong signal in the complex trees. The point is that we didn't want to use too many observations in the simulation study, which would simply slow down the calculation of the marginal likelihoods. We also see that we need at least, in this example, 30 to 40 members of the population in order to get perfect power of detecting this tree. And also we need at least correlation of 0.6 in order to be able to recover the tree having one of the leaves misspecified. Finally, we are done with the simulations and sensitivity analysis, and we can deal with real data. And the first real data application is the QTL study of the data on Arabidopsis thaliana from Sormanyan and others. So here we had 220 markers distributed over 5 chromosomes. The sample size was equal to 279 observations, and we had 4 different phenotypes. In particular, we were studying the hypactyl lengths under 4 different light conditions. And we could compare the results to the original study by Sormanyan and others. And so what we saw here is that for the phenotype under the red light, we could see several single markers that had somewhat some effects, as well as an indication of one two-way interaction. Under the blue light, we also saw an indication of one two-way interactions and several single markers detected, and the same concerns the white light and far red light. If we compare the results to the original study, we can see that for the red light, we are pretty much recovering the same markers. But of course, in addition, we could recover this indication of these two-way interaction between chromosome 2 and 1. For the blue light, we were recovering 3 of the four original markers. In addition, we see an indication of an epistatic effect between the two chromosomes. For the whites and for red light, we were recovering exactly the same markers as in the original study. We also addressed a second data example based on the Drosophila data from Zenk and others, which had 45 markers distributed over 3 chromosomes. These data had data on 2 species, in particular Drosophila simulans and Drosophila mauritana, and 5 different traits. The sample size for the first species was 471 observations, and for the second species was 491 observations. And so the original analysis was performing mapping for the backcross design. There also are some results available from Bogdan and others who were using the MBIC approach for detecting individual markers and epistatic effects. And the results for all of the traits are actually available in the supplementary materials. We managed to detect several single markers as well as several strong epistatic effects on these data. And today in the rejoinder, we're going to address predictions based on these data a little bit later. But for the main part of the talk, I think we are ready to come to the summary. So in this paper, we introduced novel model priors for Bayesian logic regressions. We also introduced a novel algorithmic approach called GMJ-MCMC, which is specifically designed to, first of all, not get stuck in local extrema, and secondly, explore a very complex space of models by means of embedding the MCMC into the genetic algorithm framework. We saw that the algorithm could outperform some of the baselines, and we have an R package available. And by the way, in the rejoinder, we are providing a tutorial on the R package for Bayesian logic regression. Among some directions for the further work, I would like to mention perhaps the most interesting and challenging is going to be to allow subsampling in GMJ-MCMC algorithm to be able to deal with tall data and large data sets in general. And also, it is still an open question of how to report the true positives for the logic regressions and what are the true positives, whether extremely correlated trees are still going to be reported separately as we do it now, or whether we should merge them somehow when reporting the results. And so thank you. Here is the literature, and I would like to give the word back to Michele.
Perfect. Thank you, Alexander. Thank you for the presentation. So we invited to discuss this paper 3 groups, Ingo Rusinski, Charles Cooperberg, Michael LeBlanc submitted a discussion that you will find in the March issue of Bayesian Analysis. We were not able to participate in our webinar. The other 2 groups of discussants, however, are here. The discussion was very lively, by the way, so I invite you to read the discussion on the journal when it's going to be available soon. So the first group was, second group, sorry, was the one by Malgorzata, Bogdan, Blazej, Miasejedow, and Jonas, Wallin. I'm going to give them the word, maybe what they can right now. Let's see, 1 second. Let me see if Malgorzata. Okay, are you?
Yes, I am here. I'm sorry for the lack of camera.
Okay, no problem. Can you see your screen?
Yes, I can see the screen. Yes.
Perfect. And Blazej and Jonas can chip in anytime. They just need to unmute themselves. Perfect. So if you can share the screen, we can go on with your discussion, and then we'll discuss. We will have a discussion by Holger, Schwender, and Katja Ickstadt.
Sorry. So I didn't present slides. So okay. should we share the PDF of our discussion?
If you have them, yes. Otherwise, no. Just.
I will just maybe comment.
Perfect. Go ahead.
So let me say that first of all, I think this is a very interesting and important paper. So logic regression is, I think, indeed a very useful tool in the context of analysis of genetic data, when the real gene influence on the trait is often specified indeed by the logic expressions. I think this is a very important paper to recall what this whole model in the context of genetic data. We very much enjoyed also the algorithmic approach, which is based on Laplace approximations, which in our opinion is an interesting, not necessarily on Laplace approximation, but also on calculating the marginal likelihood. So the marginal likelihood for every model can be using the priors which the author specified, can be accurately calculated or approximated by Laplace approximation. And this in principle allows to avoid using MCMC. Basically, each model can be visited only once, and the posterior probability for each model can be calculated by the Bayes rule. So, like the authors presented. So we are kind of like this approach. We also liked the way the priors were specified. So the priors penalize the complexity of the model, and the priors are specified in such a way that they introduce the multiple testing correction. So since the number of models of a given complexity increases with the number of variables in the database, the penalties which are introduced actually, the priors which are used in this model introduce the penalties which work in a similar way as a multiple testing correction. So all of this we liked a lot. However, we had some reservations concerning the algorithmic issues. So first of all, it seemed to us that the mode jumping MCMC might be a little bit too complicated approach for the search. So what we really need to do here, it seems to us, is to search through the class of possible models. So it doesn't seem to us that reversibility is a necessary condition. And it seems to us that a lot of effort in mode jump MCMC algorithm is indeed trying to preserve the reversibility of a model, so of an algorithm. So in our discussion, we proposed some other ways, like non-reversible MCMC, which in our opinion could provide a more rapid procedure for the search over the proposed model. Another issue which we were a kind of worried about was the treatment of tautologies. So it was mentioned that each logic expression can be actually written in many different forms. And we didn't notice in the paper, or we didn't observe how it was treated in the algorithm. It seemed to us that in many instances, the same logic expression could appear in the algorithm in different forms, which were given different posterior probabilities. And since at different stages of the algorithm, some leaves were eliminated based on the calculations of the posterior probabilities, we were kind of afraid that due to this dilution of the probability between different tautological forms, some of the important logic interactions can be actually eliminated. Another issue is we kind of didn't really understand why the final calculation of posterior probabilities were based only on the quite limited number of models searched in the final stage of the algorithm. So in the implementation which was provided in the article, the authors used like, I think about 10,000 models, did you? Which seemed to us a little, we didn't understand why, since the algorithm visits many, many models on the way, calculations of integrated likelihood is a kind of easy. We didn't understand why these values were not stored and why the whole history before reaching the final population was a kind of forgotten in the calculations on the final posterior probabilities. I think there were mainly these three main issues. Maybe I will ask my colleagues from the group if they would like to add something. Wallin?
Did you ask me? Well, the issue was also the prior, if you have the same model being non-unique, is it controlling the false discovery rate?
Yeah, so yeah. Mm-hmm. So basically we were thinking that because of the tautology issues, the number of different tautological forms of a given logic expression increases with its complexity. So I think if these tautology issues are not properly taken into account, this fact may a kind of counterbalance the multiple testing correction introduced by the prior suggested by the authors. So this is what we were kind of concerned about.
Okay.
Can I add something?
Go ahead, yes.
One other issue was with parallelization. This parallelization was quite strange way how the result was merged together. This formula for merging results from different runs was quite hard to understand. It seems not a really nice way how to do it. And we also propose in our response other way of synchronized parallel runs.
Okay, perfect. So we will give the authors the opportunity to reply after the next contribution, which is the discussion led by Katja. Katja, you want to let's see, unmute yourself? Do you have prepared the slides for the presentation? Or
oh, sorry, I did not prepare any slides. I didn't know that this was maybe.
No problem. Yeah. Okay.
Good
no
idea. So I guess I will do it the same way Gosha did it. First of all, really congratulations also from Olga and my side to a really nice paper for this important model class. Our discussion actually has sort of 4 parts, and I'm sort of trying to pick the main points in each of the parts. So the first one is sort of on fitting logic regression models and sort of comparing the new approach to the original logic regression and logic FS. And I guess in that part, the main point we raised was that for the new version, for your version, it's a Bayesian version, and so given the fact that there is not the one model in the end that's usually the best one, in a Bayesian world you would do model averaging, which is a sensible thing to do. However, out there not everybody is a Bayesian, and although I'm Bayesian by heart, others might prefer sort of an ensemble version of the new GMJ-MC-MC method. So that would just be a suggestion to sort of broaden the paper for audiences beyond Bayesians. So that was sort of the first point. The second chapter in our discussion is on comparing GMJ-MC-MC with another sort of genetic programming for association studies that we did sort of parallelly to working on our logic regression and logic FS sort of approach. And the main point tackled there, I guess, is the fact that for our approach, what we use is we use the logic expressions in their so-called disjunctive normal form, which means the logic expressions are all written as or combinations of and combination. This is, I mean, this has maybe two different arguments to it. One is interpretation. I mean, it's really easy to interpret the end combinations as interactions in a statistical sense. And the other thing is that with this disjunctive normal form, you don't run into this problem what Alexander, you described with the non-Boolean equivalence. So sort of the shortest disjunctive normal form is sort of a unique way of writing a logic expression. So that was sort of one point we made in that part of the discussion, and maybe you even also did use this disjunctive normal form in your version of GMJ MCMC. I just don't know, it wasn't clear to me from the paper. This disjunctive normal form then also could maybe be used to define the prior for the trees, to sort of get the complexity sense for defining prior for the trees. So that was sort of the second second point we raised. The third one is assessing the importance of identified interactions. The authors suggest to use the marginal inclusion probability for the logic terms given Y for inclusion of the logic terms in a model. The downside of this is that it sort of is not independent of new data. And so another idea is used in the logic FS version of logic regression, and there bootstrap samples are applied. And then what you do is you look at the bootstrap samples, you look at your logic expression being in the model for one part of running the bootstrap samples and not being in the model for another part, and then just looking at the difference for the two models and seeing how both do in terms of, for example, calculating the correctly out-of-bag observations. And so that could be a way of assessing the importance for interactions in MJ, MCMC also. So that would be a suggestion to at least compare it maybe to marginal inclusion probabilities, or at least leave it as an alternative to it, since it does rely on independent data. So that was sort of the third point. And the fourth point was the one that you already touched, Alexander, the one with the very high odds ratios in your scenario 3, for example. You mentioned in the presentation today that you had chosen these unrealistic effect sizes due to being able to use small sample sizes. However, they are really, really large, and sort of when reading it, the question remains, is it really necessary, or is it just so to sort of cut down on sample size? Or is there something else lying underneath that, like a breakdown point or an effect size independence of sample size that needs to be matched, something like that? That's at least, as a reader, you would wonder about these questions. I'm pretty sure that's not the point. It's choosing these effect sizes so large, it just makes the reader wonder, is there something strange behind it? I don't think there is, and it might be worth pointing that out. Yeah, I think these are the points from our discussion. Thank you.
Perfect. Thank you so much, Katja. Okay, so as I was saying, there has been another discussion by Ingo Luzinski, Charles Kupperberg, and Michael LeBlanc. They provided a brief introduction to the topic of logic regression and its development. They also pointed out some, they also discussed the GMJ MCMC algorithm. And they basically, one important point that I would like also to have the authors a feedback about is that they were commenting on how this algorithm puts a prior on model size and therefore depends crucially on the definition of model complexity. And I wanted to have their take about it. But without further ado, I'm going to first leave the word to Aliaksandr and the other author to reply to the points made by the discussants.
Thank you, Michele, and thank you all of the discussants. So today, now I'm going to present the overview of the critical and other points made by all of the discussants. And then I will provide some additional simulation studies and prediction-driven examples and a summarization of this rejoinder. And so to begin with, I'd like to address the points made by Ruchinsky and his colleagues. So the first point that we found to be interesting was that the objective of using the product of the marginal likelihood and the prior could have been used in their simulated annealing algorithm and perhaps would have improved the results of the inference based on the simulated annealing algorithm. And this is actually a very interesting point, and we definitely agree that it could lead to very interesting results. It is also related to this comment by Bogdan and her colleagues on the possibility of using parallel tempering approaches for MCMC and change in temperatures for different threads of GMJ MCMC, which might work as a way to further improve the quality of the inference. Another point made by Ruchinsky was that definite logic regression currently is not being used only for the genetics, but is being used in many other applications. The same point was actually made by Bogdan and her colleagues, and we discussed this a little bit in the rejoinder. They also suggest a very interesting approach of firstly testing the general null hypothesis of whether there is at all any relations between the responses and the predictors. And only if there is an indication of some signal, one would then be recommended to proceed with the inference using, for instance, GMJ MCMC on Bayesian logic regression. And this actually is a very good idea that can save a lot of computational resources because Monte Carlo inference is computationally costly. Ruchinsky and his colleagues also wonder about the performance under the correlated scenarios. And I've already mentioned today that even though in the simulation scenarios we addressed in our original paper, we had marginally independent predictors, already two-way interactions and three-way interactions and even four-way interactions would be extremely correlated. So the algorithm is actually dealing with the correlated data very well. And by the way, it's not allowing any tautologies. And we clearly have written that in the paper, but today we're going to provide several additional examples on the correlated scenarios. Also, Ruchinsky and his colleagues wonder about the non-logical covariates and whether they can be included in the model. And this is a very interesting suggestion. So we suggest an extension of the logic regression model in the rejoinder and also show the performance of the GMJ MCMC algorithm under the case when we have both logical predictors and non-binary predictors combined. We provide an example of inference on such models in the tutorial section of the rejoinder. Finally, Ruchinsky and his colleagues wonder about the parameter choice of GMJ MCMC algorithm, and we address this again in detail in the rejoinder and also give some hints in theorems 1 of the main paper and also theorem A1 of the supplementary materials. We have the study on the dependence of the population size in the sensitivity analysis. Schwender and Ickstadt suggest an interesting alternative of the GMG-MCMC algorithm, which is a generic programming approach for association studies, which is using the logical expressions in the disjunctive normal forms. And this is definitely a sound approach and an interesting approach. However, we believe the comparisons for further research, mainly due to that in this paper we were mainly focusing on the Bayesian approaches to logic regression. So we didn't include any comparisons to, for instance, simulated annealing algorithm that was originally suggested by Ruchinsky and his colleagues. Another point by these discussants was that one can, in principle, quantify the importance of particular logical expressions based on the unseen data. And whereas we do not directly do this in the rejoinder, what we are doing is that we are addressing a predictive example where we are showing how the logic regression can be used for predictions. And of course, once one is recovering the data generated model, for instance, then of course the predictions also going to be close to perfect. This is pretty much the same comment that, I mean, one could use this logic feature selection approach, which is very interesting. However, we didn't have the capacity to address this in detail in the rejoinder. Finally, regarding the large effect sizes, this is something that we have already discussed today in the sensitivity analysis. So, I mean, as we can see here, we need to have enough power or strength of the signal in order to at all have these tree detectable. And this can be either achieved by means setting a large effect size. In principle, an alternative would be to set effect size to somewhere here, or even here, but then increase the sample size, because there is a direct dependence, both theoretical and in terms of the simulations between the strengths of the signal and the size of the samples, at least for the Gaussian models. And so, of course, I mean, we just need to have the tree detectable in theory. And in order to have the tree detectable in theory, we want to have a strong signal size. Of course, if we set a lower signal size and increase the sample size to 10,000 observations, that would definitely work in exactly the same way. The problem is that calculating the marginal likelihood on 10,000 observations is a bit more costly than calculating it on 1,000 observations. And the point is that we ran 6 simulation scenarios on 32 cores each, and also had 100 replications of each of the scenarios. And this was done for 2 different priors. So, I mean, that would just take a little bit more time. That's why we used somewhat larger effect sizes. Yeah.
Alexander, can this be cured to some extent anyway by a 2-step approach? It's not the exact same model anymore, but it might make it faster.
You mean? I didn't. You mean? I mean, the 2-step approach was suggesting first testing if there is at all any association,
yes,
and only then running logic regression. But the point is that there one tests the association to the leaves. I mean, to me, it's not really obvious if then it would actually allow to directly test whether there are any 4-way interactions. So it might work actually, but I'm not sure about this.
Just thought maybe you can sort of cut down on some of the sort of on model size a little bit, and then increase sample size accordingly, but on sort of.
Yeah. This we could have done, like kind of reverse engineering, but we just didn't want to go for this kind of reverse engineering. So we just specified these in facts and then tried it out. It worked. And then we did sensitivity analysis to show that there is some dependence, of course, and you need to have enough signal to be able to detect it, especially for the complex trees. And of course, it would be very nice as further research to provide some theoretical support of kind of dependence on the sample size and strength size to be able to asymptotically recover a particular tree under, for instance, our prior using the algorithm that we are using. But this is something that we didn't do in this paper. Okay. Okay. Thank you. Did it answer the question?
Mm-hmm.
Great.
Yeah.
Okay, so then we had the discussion from Malgorzata, Bogdan, and others. And the first point that they made was that the BLR seems to be particularly useful for analysis of outbred populations where the markers are independent. But we actually do think that that definitely would work for the outbred populations, but definitely the approach is not limited to them. We will show in the rejoinder today that the approach works extremely okay, even for the heavily correlated markers. The other concern was the lack of treatment for tautologies, which in fact is not true. I mean, back in the original paper, we described the thing that if we are generating a new tree, which is 100% correlated to some other tree in the population, we are just selecting one of those trees which has a simpler logical expression in terms of the logical size of the tree. And that tree only makes it to the next population. And so we are simply not allowing the tautologies in the algorithm. When it comes to the tautologies in terms of the prior, this is a different point. And of course, we are still using an approximation of the number of trees, but we are not dealing with those tautologies indeed in more detail there. On the other hand, for every particular logical expression, we have this natural symmetry of the tautologies that appear that should, in principle, to some extent, cancel this effect out. Regarding the sum, they also had a comment on that in the sum of the denominator of the renormalized estimator of the posterior model probabilities, one only uses the models accepted by MGM-CMC. That's simply not true. So it includes all of the models addressed, and this is addressed in the rejoinder also, and also written in the original paper on MGM-CMC. They wonder about the treatment of correlated predictors, and we're going to deal with this issue today. And finally, they wonder about the value of the sum in the denominator of the renormalized estimator, which indeed, by one of the options, is only including the models from the last populations. This is just done for the computational reasons as one of the approaches, so we can use all of the previous, of course, models that were visited by all of the threads of GMGM-CMC algorithm. This is, of course, not needed in theory, but in practice, we have this super exponential growth of the number of models with respect to the size of the logical trees. And one has to do some pragmatic assumptions and pragmatic decisions in order to not work with too large hash tables, for instance, or other data structures, and avoid writing and reading from disk too much as just some practical iterate things. Another comment was that they didn't like the way we're merging the results from the parallel threads. And then they suggested the formula that we suggested in the paper. I mean, in the paper, we suggest two approaches. The first approach is to merge all of the unique models from all of the individual threads of GMGM-CMC algorithm and use them in the denominator of the Bayes formula, right? This, however, would need us to transfer statistics and all of those models between the threads. And I don't really like to transfer a lot of data between the threads. And the second approach, which is having exactly the same asymptotic guarantees, is to just using some weighting schemes that we suggested. And then one only needs to return one value from individual tree for the parameter of interest from the individual thread, which is computationally more efficient. Well, another comment that arises today is that is not depicted here is that one could use some kind of synchronization between the threads. It might work, but in my experience, implementing embarrassingly parallel programs work normally a little bit better than the kind of synchronizations. Though in theory, I mean, good synchronization should speed the inference up. In practice, it often happens that it just slows the things down. And we give some references to such cases in the paper. Finally, we had a contributed discussion from Clarté and Robert, and they had some really strong points and criticized the Jeffreys prior, and we definitely do agree that using the improper priors is quite debatable. We used this discussion already in the original paper, and of course our theoretical preference is with the robust G prior. And we also have to emphasize that normalization for the marginal likelihoods we discussed in the original paper on MGM-CMC in Formula 14 and below. There were somewhat misleading presumptions regarding the MGM-CMC algorithm that we answered in the rejoinder. So first of all, I would like to mention that MGM-CMC algorithm is a proper metropolis Hastling, and it has the asymptotic ergodic distribution which corresponds to the marginal model posteriors. And it also has the guarantees of unbiasedness and consistency of the posteriors in the limits. It also is not incorporated any ideas of the taboo search. And this was a somewhat comment which is contrary to what, for example, Bogdan and her colleagues said. So actually, Clarté and Robert wanted the algorithm to be reversible and thought that it was non-reversible. But the MGM-CMC algorithm is definitely reversible, and it's not incorporating any of the ideas of the taboo search. So it can, in principle, visit the same models several times, which on one hand allows it to escape from local extrema and explore the model space better. On the other hand, it, of course, requires to revisit the same models, though we are saving the results on all of the models in the hash tables, and we don't have to recalculate the marginal likelihood or re-estimate the posterior modes, for instance, of the parameters.
Alexander asked a question.
Yep.
You say that MGM-CMC is reversible, but do you have any results that genetic modified MGM-CMC is reversible? Because this genetics most does not seems to be reversible with respect to posterior.
Well, it is reversible. It's not reversible in the sense of that it doesn't satisfy the detailed balance equation, but it can visit the same model several times.
Yes, but
different populations. So, but it is not reversible. In our new paper, and there is a preprint on archive entitled Deep Bayesian Regression Models, we give an extension of GM-CMC algorithm to our GM-CMC algorithm, which also uses these jumps between the populations of trees, but that algorithm is actually reversible, but not GM-CMC.
So in
Here,
the final algorithm is not reversible, but yes?
Yeah, so GM-CMC is not reversible, MGM-CMC is reversible.
Okay, thank you very much.
Yeah. Okay, there was also a comment on the practical choice of parameters for the algorithm, and we already discussed this issue beforehand during this rejoinder discussion. Finally, the last point was that whether one can define some priors that can deal with imbalanced binary covariates. And this actually is a very interesting idea. This hasn't been addressed in the previous versions of priors for Bayesian logic regression, and this hasn't been addressed in our priors, though we are not really sure how easy it could be for complex logical interactions to account for imbalanced covariates. So we leave this for further research. We are going to continue to present the rejoinder with some additional simulation studies. And here we address the simulations with correlated predictors. So we addressed exactly the same scenario 5 with exactly the same unit dispersion level for the Gaussian observations, and the mean defined with respect to some single leaves, two-way interactions, three-way interactions, and four-way interactions. But in addition, in the first sub-scenario, we generated correlated now predictors. So x's are correlated with the correlation level, which was varying from -0.4 to 0.4. And for the second sub-scenario, we use this QTL structure of the correlations, where the neighboring markers could have correlations of above 0.9 even. Right, so this is a heavily correlated data example, and then we have presented the results. So for the weak correlations, both the inference under the Jeffreys prior and the robust G prior worked very well. So we exactly have the same pretty much power for the single leafed trees, two-way interactions and three-way interactions. We have somewhat lower power for the four-way interaction, but the overall power is still very high, and we still have acceptable level of false power rate and very small number of wrongly detected leaves. There is very similar performance to the independent case here. If we have these extremely strong correlations, we still can see that the results are okay. So I mean, we still have very strong power at detecting these one-way interactions, two-way interactions, and three-way interactions. Though the power of recovering the four-way interaction drops, this means that one perhaps would need more parallel threads of GMG-MCMC or running the inference a bit longer to increase the power somewhat. But of course, I mean, there is much more noise here, and it's just a more complex problem. Still, we have a reasonable level of the average number of false positives, yet we have here much more wrongly detected leaves in 100 simulations. So because of those heavy correlations between the neighboring markers, we were quite often detecting neighbors of the original leaves instead of the leaves themselves. And in many of the QTL studies used in practice, actually both neighbors and the original markers are counted as true positives, even though here we have been sticking to the most conservative approach, and we're only counting the data generative trees as true positives. And well, here we come back to this last point in the discussion of the main paper that, I mean, one has still a little bit of flexibility of what is going to be reported at the end of the day, and whether extremely correlated trees should be merged together or not. But we leave this for further research. Right, so these were the results for the additional simulation studies. So also Ryczynski and his colleagues wondered if the approach can deal with non-binary covariates, and we suggested an extension. This extension actually was already implemented, so we didn't have to do anything in terms of the algorithm, but here we are allowing model selection for additional Q-marked non-binary covariates. And then one, of course, has to update the priors, and we additionally are introducing this Bernoulli type of penalization for the non-logical covariates. We can rely on exactly the same theory for calculating the marginal likelihood for this case, and also adopt easily GMG-MCMC algorithm where the non-logical covariates simply cannot be part of logical trees. And this approach is implemented, and we have shown the results of inference using this approach in the tutorial section of the rejoinder, where we got perfect recovery of the data generated process as well. Finally, the last extension that we suggested in the rejoinder was allowing for the Gaussian latent variables, where in addition to these non-binary variables, one introduces latent Gaussian variables, deltas, which are taking care of special temporal relations between our responses y, and allow us to generalize the model and account for correlations between the observations. Here, one has to update the parameter priors to be able to make them compatible with the integrated nested Laplace approximations. And here, obviously, the marginal likelihoods are computed efficiently by the Inler approach and would be exact for the Gaussian models with Gaussian observations, and otherwise will only be approximates. Finally, we predicted a classification of the two species of Drosophila. Particularly, we differentiated between simulans and Mauritania species. We ran here one thread only of GMG-MCMC algorithm and used Bayesian model averaging of individual posterior probabilities on the test data for predictions. We also compared, we divided the data into test and training data with 100 different random splits of the same size. And we compared the results for all of those splits across different approaches, including some linear models like Reach, Lasso, linear regression, Bayesian linear regression, linear boosting, and some nonlinear approaches like artificial neural networks, tree-based boosting, and random forest. Here we are reporting the medians for the accuracies, for the false negative and false positive rates, as well as the bounds. And we clearly see here that BLR performs here well, on par with the best performing approaches. And the interesting message here is that apart from the BLR, only linear regression approaches are performing well, whereas nonlinear models like neural networks or random forests are having a bit worse performance. And we were wondering why. And we of course know that BLR is robust to either having or non-having nonlinearity. So if there are no interactions between the logical predictors, then we're not going to detect them. And if there are, we're going to detect them. And here we just looked at the posterior inclusion probabilities, and we saw that only linear effects were of interest, and hence, not surprisingly, the linear models performed better than the nonlinear models, which somewhat were overfit into the train data subsets. So that was pretty much it for the rejoinder today. So we get a recap of MJ-MCMC algorithm additionally in the text of the rejoinder available in the journal. We report all of the details on the simulation scenarios with correlated data. We describe these extensions of Bayesian logic regression model and give an extensive tutorial on using the package. So thank you, everyone. Thank you for your attention. Thank you for very interesting comments and challenging remarks and questions. With this, I would like to conclude my part of the talk and give the word back to Michele.
Thank you, Alexander. So let's see if there is any further comment either from the other panelists or from the attendees. I believe the attendees can raise their hands and then I can give them the possibility to talk.
I would still have one question, but
go ahead.
So I'm still wondering whether you do actually use the disjunctive normal for representation.
Oh, yeah, that's a good point. No, we are not using the disjunctive normal representations in our approach. That would be a way actually to perhaps somewhat improve the priors and simplify the way of dealing with tautologies. On the other hand, that might complicate traveling between different modes for the algorithm a little bit, because then you have a somewhat smaller search space, and then perhaps going between some of the modes would be less would be more difficult. But no, we didn't do this for now, at least. Yeah.
I just thought it might be more stringent to actually do it, because then you do not run into problems you might run into when allowing for other representation.
Yeah, but as I mentioned, even though we are not doing this in the algorithm, I mean, we are not allowing two of the same representations of the same tree to enter any of the populations. They can only be in parallel threads. So in different parallel threads of JMC, we can have different representations. But then when we are merging results together, whenever we are selecting the simplest form, which will typically correspond to the actually also the disjunctive normal form.
Yes. Okay.
Excuse me, so maybe I have a comment concerning these tautologies, which we actually ran the algorithm, and in the output we observed 5 different replications of the same interaction, which were different only in the number of brackets between different x's included. So could you explain on this, or how would you summarize the result?
That shouldn't happen. You might send the example to me.
Okay.
But this, in principle, shouldn't happen, because at the end of the day, we have this simplification function which should merge all of the equivalent trees together.
So this is just to explain why we commented so much on the replication, because we actually observed it in practice. Okay, we just ran the algorithm and observed the problems. Okay.
I would like to add one more comment. We do not propose to use parallel tempering. We just propose to use different acceptance ratio to better explore the space of trees.
Yeah, but this is exactly the same as tempering at
We
the.
leave out the part of the proposal. We just do not care about what we propose and just the proposal is reversible or not. We just want to look
Okay, wait.
how you increase probability or decrease and just make a cutoff of the model which you accept.
Yeah, that could be a viable approach to try if one wants.
Oops. What's going on? Okay. So
probably just one comment. Well, the whole thing with the brackets, this is something from the output which we are also hoping in the future to work on, because the output with the brackets, it is difficult to read immediately. So this will in the future hopefully be made somewhat more user-friendly.
So the problem which we're kind of worried of is that there were just 4 different versions of the same interaction with, I don't remember, 2 or 3 x's, which were different only by the number of brackets and had different posterior probabilities, which were not, you know, this is why we were thinking that you have that application problem.
Well, maybe,
okay, but maybe we just, yeah.
We can look at this example, but it might well be.
But this should be possible at all. Well, I mean, of course, this should be possible due to some bug, but it shouldn't be possible in principle, because we at the end of the day check the correlated trees and merge them together. But of course, I mean, should you provide this example, I will definitely look into that.
Sure.
I didn't face those examples myself, so we have still a limited number of tests in a way, so there can be some reliability issues, of course.
I mean, the question is if they're also really the same, exactly the same logic expressions, because I mean, with the brackets, they just might be actually not exactly the same.